Hey everyone, welcome to another session of Ceerazzledazzle Physics. In today's session, guys, I'm going to be walking you through the entire GCSE Physics Electricity topic. And before we get going, guys, make sure you hit the like and subscribe button to keep my channel going. I've got hundreds and hundreds of videos to help you with your studies. Check them all out if you're still struggling. Okay, let's get straight into it. Okay, so static electricity. First of all, let's take a jumper and a balloon. Initially, hopefully you can identify that they are both insulators. Yes, so no charge can actually flow through them. And they are initially neutrally charged. That means that they have equal amounts of positive and negative charge. So look, the jumper is positive over here and negative, equal amounts. They cancel each other out. And the balloon as well, 3 positive, 3 negative. They are both neutrally charged because they also cancel out over here. But if you were to rub them both together, what happens is charge can be transferred from one form to another. So look, you can see that the balloon has gained these negative charges over here, which are the electrons. And the jumper over here has lost the electrons to the balloon. So the object which loses the electrons becomes positively charged, and the object which gains electrons becomes negatively charged over here. Right, so now look, this one is positive and then this one is negative. So they've now become charged. And this is the origin of static electricity because now they've both become charged. The charge is not free to flow and therefore it's stuck on the balloon and it's stuck on the jumper over here. Right, so now from here we're going to do the following. We can now hopefully explain why a balloon, if you take it and you rub it against like a jumper, why it can stick to a wall. So over here, let's say the balloon, we charge it, and obviously it's negative charge, and then you were to place it next to a wall over here. Hopefully we can see that. Look, what happens is within the wall, the negative charges get repelled away. Obviously because these ones are negative, they repel these ones away. And therefore the positive charge attracts the negative ones on the balloon, and that's the reason why the balloon sticks to the wall. Hopefully you've seen it as a party trick yourself, and obviously try it yourself. Like take a balloon, blow it up, rub it against your hair or your jumper, and you'll be able to stick it against the wall based upon this principle. Now a use of static electricity can be the following. Let's say you were to paint a car efficiently. So what you can do is this, you can charge the car positive. Yes, so you would attach it to a terminal and it becomes positively charged, and you charge the paint negative. Then you spray the paint, obviously positive and negative, they will attract, and therefore they will stick evenly across the car. So this is a great way to use static electricity to paint a car. Electric shocks. So let's say over here we have a cloud and it's full of electrons over here. The cloud is full of electrons and you're flying a kite. First of all, hopefully you can identify that the electrons over here will want to like discharge itself. And that's the reason why we get an electric shock. So this spark occurs from there going all the way down. The reason why is because there's a large potential difference from the cloud and yourself. And that's what causes the spark. And in this case, it's the lightning strike. That's why you see the lightning over here, because it's trying to discharge itself because all the charge builds up. And that's the reason why we get an electric shock. It's because there's a large potential difference, hence why the charge jumps from one place to another. An electric field is going to be the following. It is a region in space in which a charged particle experiences a force. So look over here, we've got two electric fields. This one's a positive one, and look, the arrows are going outwards. Negative one, the arrows are going inwards over here. The direction of the field tells you that if we were to put a positive charge here, it will move along that line. If I were to put a positive charge here, it moves along this line. So the direction of the field lines tells you the direction in which a positively charged particle will move in. This one is a uniform field. The reason why is because the lines are evenly spaced out here. Like school uniform, it's evenly spaced. You know, everyone's the same idea. 1, 2, 3, all the lines are evenly spaced. This one's a uniform field. The previous one over here, this one is a radial field. The reason why, we can hopefully see that the closer you are to the center, to the actual object itself, the stronger the field will be. The reason why is because the density of the field lines indicates the strength of the field. So over here, because there's loads of field lines in a small bit of area, that's why the field is stronger. But the further away you are, the less strong the field will be. Okay, so now electrical circuits. So we've got to be able to identify the electrical components and the different symbols. So look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different electrical symbols. Open switch, closed switch, lamp, diode, LED, cell, power supply, fixed resistor, variable resistor, fuse, thermistor, LDR, ammeter and voltmeter over here. So all of these ones over here. Make sure that you are able to draw them and identify them in a circuit. Okay, so electrical current. So current is simply the rate of flow of charge. Current flows from the positive terminal, the long stick, to the small one going all the way around over here. If you want to measure the current of a component going through it, right now, look, you place the ammeter in series with it. The ammeter is placed in series. So the formula for the current is equal to the charge divided by time. I is equal to Q divided by T. I is measured in amps, the charge is in coulombs, the time is in seconds over here. There we go. Right, so this is called conventional current because the current is moving from the positive terminal all the way around to the negative one. Right, so you might be asked about the electron flow in this diagram. So electrons don't move from the positive terminal to negative. If you were to look at this diagram, you can see that the electrons are going from the negative terminal to the positive one. The reason why? Because the electrons are repelled from the negative terminal. Obviously, the same charges repel and attracted to the positive one over here. So conventional current goes from long stick, positive to negative, but the electron flow is actually in the opposite direction. Right, voltage and potential difference between 2 points. So the voltage is simply the energy per unit charge. Voltage is equal to energy divided by the charge. V is equal to E over Q. That's going to be our formula. The units, voltage measured in volts, energy is in joules, charge in coulombs. If you want to measure the voltage of a component, you place it in parallel around the component over here. So look, it's placed in parallel around the component. There we go. Right, now current in series and parallel circuits. So the rule for current is going to be this. Current in a circuit, it splits at the junction. So that means that the total current going into a junction is equal to the total current out of the junction. So look, there we go, the current comes in, it splits and goes there and there. So therefore, then look at this point over here, these two combine together to make this one over here. So look, you can say that the total current going in is equal to the total current coming out at the junction. So look, this one, IT is equal to I1 plus I2, which is this one over there, and I1 plus I2, as they both recombine, they will make IT over here. Easy stuff. Voltage in series and parallel circuits. The total voltage into a loop is equal to the total voltage out of the loop. So look over here, the sum of the voltage in is equal to the sum of the voltage out in one complete loop. That basically means this. Look, we've got one loop there and one loop over here, back to the center. So look, V in is equal to V1 plus V2. Yes, over there. And also we know that the V in is also equal to V free. So this voltage across here is the same voltage across this one over here. Required practical, voltage and current characteristics of a fixed resistor. So in order to look at the voltage and current characteristics of a fixed resistor, you need the following circuit. You need a power supply, fixed resistor, variable resistor, the ammeter placed in series, and the voltmeter placed in parallel. Right, the method, so obviously set up as shown, then obviously turn on the power supply, and then record the values of the voltage and the current, yes, from the voltmeter and the ammeter. And then you change the variable resistance over here, which will affect the current in the circuit, and then you repeat again, recording the voltage and the current again. There we go. Control variables, keep the fixed resistor the same throughout the entire investigation. Yes, keep the power supply voltage the same each time. You're only changing this the variable resistor over here, and recording the voltage and the current of the fixed resistor. Then if you were to plot the graph, you'll recognize that you get a straight line relationship between the voltage and the current over here. Risk assessment, obviously, turn off the power supply in between readings to stop the fixed resistor from overheating as well. Right, now once you've done that, you can then look at the voltage and current characteristics of a filament lamp. So look, it's the exact same circuit. I've just swapped the fixed resistor for the filament lamp. You do the same thing again. You simply just going to change the variable resistance over here and record voltage and current. You end up with the following graph now. So look, it curves off over here. Right, so making sure that you can explain this graph. The reason why you get this S shape is because the lamp starts to heat up the more and more current you pass through it. As the lamp starts to heat up, what happens is the resistance increases. If there's a resistance increase, what happens is the current obviously has to stop increasing. Not decrease, but stop increasing over here. So the reason why the current starts to level off is because the resistance is increasing. Make sure you can recognize that the filament lamp results in this S shape over here. Right, so once you've done that for the filament bulb, you can then do it for the diode. So look, it's the exact same circuit, and what you're going to do is you're going to change the variable resistance and record the voltage and the current over here. And you'll get the following graph, guys, so there'll be no current in one direction, and look, after a while, then the current then starts to increase. So make sure you're happy with this graph as well. So looking at them all together, we can see for the fixed resistor, we get the straight line directly proportional relationship. For the filament bulb, we can see that it curves off over here. For the diode, we can see that it doesn't work in a one direction, then it starts to go up. Make sure you can understand that for the fixed resistor, voltage is proportional to the current, yes, and therefore you can actually say that V is directly proportional to I, and this leads us to Ohm's law, which is going to be the voltage is equal to the current times by the resistance over here. V is equal to I times by R over here. And look, we talked about the filament bulb. The reason why it levels off is because the resistance increases. I'll put that on the board. And the diode is quite important because It only works if it's a certain way around in your circuit. If you put it the wrong way around in your circuit, the current will not flow through it. So if you, over here, you can see that there's no current because it has an extremely high resistance in this direction. That's the reason why. So it has extremely high resistance in this direction. And over here, there's a threshold voltage before the current can flow. Right, so now combining resistors. If you want to combine two resistors together, let's say you had R1 and R2 over here. You want to draw another circuit, combine them together. You simply add them together. So R1 plus R2 is equal to RT over here. And here's an example, 10 and 20 ohm resistor. Add together, it's going to be 30 ohms in total. Right, if you want to combine them in parallel, so look, these two are now connected in parallel. If you want to make them into one simple circuit over here, you can do 1 over R1 plus 1 over R2 is 1 over the resistance in total. You're not required to know that formula, but just be familiar with it. Right, so let's look at this example. Let's say I have a 10 ohm resistor and a 20 ohm resistor connected in parallel. Look, in terms of the maths, 1 over 10 plus 1 over 20 is equal to 3 over 20. Over here, yes, cross multiply, therefore 20 over 3. The equivalence resistance, these two combined together make 6.67. Yes, there's less resistance combining them together. Right, and therefore to summarize, hopefully you can identify that combining resistors in series, look, it will obviously give you more resistance than if you were to combine them in parallel. Yeah, comparing the left-hand side to the right-hand side over here. Right, then, required practical, factors affecting the resistance of electrical circuits, combinations of resistors in series and parallel. Right, so you say like a cell, you have resistor R1 and R2 connected to an ammeter and return back again. You then place the voltmeter around both the resistors. Then you were to record the voltage value and the current value, and to work out the resistance, the total, you simply do the voltage divided by the current over here. Then you do the same thing for a parallel circuit, so you take the cell, then you have R1 and R2, you have the ammeter returning back again. You put the voltmeter around the parallel combination bit. And notice that you record the voltage again and the current again. And then you work out the resistance by doing V divided by I. And notice, look, the resistance will be 25. So look, obviously there's less resistance when they're in parallel compared to when they're in series. So once again, summary, combining two resistors in a parallel combination will have an effective resistance lower than the two resistors connected in series. Required practical 3. Factors that affect the resistance of electrical circuits. The length of wire at a constant temperature. So you're going to change the length of the wire and you're going to see what happens to the resistance of the wire. So you need a power supply, an ammeter, a voltmeter, the wire itself, crocodile clips, and the wire should be attached to a meter ruler. Yes, a meter ruler over there. So you set up the circuit as shown in the diagram. Change the length of the wire. So you move the crocodile clips, you change the length of the wire. And what happens is you're going to measure the voltage from the voltmeter and the current from the ammeter over here. And then you're going to calculate the resistance by doing the voltage divided by the current. Obviously, and then you're going to put that value into your resistance here. Look at your table of results. You'll change the length, voltage, current, and the resistance over here. And then once you've done this, the resistance, don't forget, you can measure the length because it's stuck on the meter rule. And then the control variables is going to be the thickness of the wire. So you have to keep the thickness of the wire the same. You keep the surrounding temperature the same as well. The risk assessment, turn off the current in between the readings to stop the wire from heating up. So you turn off the current in between the readings to stop the wire from heating up. And finally, you plot the graph of resistance versus length. Hopefully you recognize that there's the length of the wire increases, the resistance of the wire will increase. Think about it like a road. The longer the length of the road, the more traffic there will be along the road. And resistance is the idea of traffic. Okay, so next thing. Thermistor then. What is a thermistor? A thermistor is simply a resistor which depends upon the temperature of its surroundings. Think of the word thermistor, so thermal resistor. And you get the following graph over here. You can see that as you increase the temperature, the resistance drops down. This is called a negative temperature coefficient thermistor. Why? Because it's going down. It's negative temperature coefficient. So as the temperature increases, the resistance decreases. So as the temperature increases, the resistance goes down. Now let's look at it in a circuit. So over here we've got a cell, I've got a bulb, and I've got the thermistor. So look, what happens if the temperature of the surrounding increases? If the temperature of the surrounding increases, the resistance of the circuit will drop down. If the resistance drops down, therefore the current will increase, and therefore the bulb will shine brighter. So make sure you can use a thermistor in a circuit, you know how it will influence the rest of the components. And by symmetry, if the temperature of the surroundings decreases, obviously we know that the resistance will increase and therefore the current drops down, therefore the bulb will get dimmer. So make sure you can use this graph when you're tackling those questions over here. Next one, the LDR, the light dependent resistor. So light dependent resistor, very simply, it's going to be a resistor which depends upon the light upon it. So look over here, it's a rectangle with two lines going into it. This is a NTC LDR, negative temperature coefficient LDR. You can see as the light intensity increases, the resistance drops down. Yes, so as light intensity increases, the resistance drops down over here. And look at it in this circuit over here. So what happens as the light intensity of the surrounding increases? If I increase the light intensity, what happens is the resistance drops down, therefore there's more current, and therefore the motor will spin faster. Make sure you can see that, yeah? And obviously, as the light intensity decreases, yes, the resistance increases, the current decreases then, and therefore if this motor gets less current, it will spin slower. Direct current now. Direct current is simply current flowing in one direction only. This usually happens in batteries and cells over here. So look, the current will go in the same direction all the time. If I was to plot a graph of voltage against time, the line is a straight horizontal line because it's never changing direction. This is going to be direct current. Alternating current is simply going to be this. The current will go one way around the circuit and then it will reverse. And then it will reverse again. So it keeps swapping directions. So alternating current, the current changes direction. It goes one way and then it swaps around. So look at our graph of voltage against time right now. We can see the current goes one way, then reverses each time over here. So this is going to be the graph for the AC supply. For an AC supply, the voltage time graph looks like this. Alright, plugs right now. So we've got three wires right now. We've got live, earth and neutral. The live wire is brown and it brings the charge into the device and has a potential difference of 230 volts. The blue wire is the neutral wire and it's going to the left hand side over here and it carries the charge back down to the plug over here. It has a potential difference of 0 volts. The striped green and yellow wire, this one over here, is the earth wire and this is a safety wire and it has also a potential of 0 volts. A nice way to memorize which way the wires are going is because if you take the second word of the color, look, second word of brown is R, sorry, second letter of brown is R and T top, L left. You can see where this one goes to the right, this one goes to the top, this one goes to the left over here. The wires are made up of copper because they're a good conductor of electricity and each of them are plastically insulated, obviously, so therefore they're not going to touch each other. The fuse is a very thin wire which melts if the current is too high and therefore it breaks the circuit. There are different types of fuse ratings, guys, and look, it's found over here. Look, the fuse is over there. There's different types of fuse ratings: 3 amps, 5 amps, 9 amps and 13 amps. The fuse rating tells you the current in which the fuse melts. So if you put 3 amps into a 3 amp fuse, it will melt it straight away. So a good idea is going to be the following. Let's say we had a kettle which uses 8 amps. Which fuse do I take? I choose the 9 amp fuse, yes? So you choose one just above it over here. For a kettle that takes 12 amps, I would take a 13 amp fuse. If the kettle had 5 amps, obviously I can't put the 5 amp fuse in because obviously it just blows straight away. So I must choose the 9 amp fuse for a 5 amp kettle. How does the earth wire work? Right, so how does the earth wire work? So over here, look, this is a toaster over here. And what happens is we've got a live wire going in and this is the heating element of the toaster. And then we've got the neutral wire going back out again. Right, so this is the toaster working fine. So let's say for by accident the live wire becomes loose and touches the metal case. What will then happen is obviously the charge will then build up upon the metal case because the case is made out of metal. So that's obviously going to be dangerous because if you touch it, you're going to get a shock because it has a high potential difference and you will have a low one, it will jump onto you. So the following is helpful. They attach an earth wire to the metal case. The reason why is because now the charge can flow. All those electrons can now flow through the earth wire down it back to the plug over here. So that's the function of the earth wire. In case the metal case becomes charged, it now has an alternative route to flow through it back to the plug, keeping you safe. Oscilloscope traces. So over here, this is the best way to visualize signals. So basically it's like a piece of graph paper, but they haven't told you that the vertical plane is going to be the voltage, the horizontal one is going to be the time over here. Each square, it will have its value. So you can change the value of each square in terms of the voltage. So it will be either volts per division going vertically or time per division going horizontally over here. Right, so here's a good example of actually using the oscilloscope trace. Let's say we have an AC supply over here and look, it's set to 2 volts per division. That's why every square is worth 2. And each horizontal one is 5 milliseconds. So the time one is 5 milliseconds. So if you want to work out the frequency, it's 1 over the time period. The time period is obviously going to be the time taken for it to go up and down here. So obviously 5, 10, 15, 20 milliseconds is the time period. That's why I put it over there. That's why 20 milliseconds, convert to seconds, 20 times by 10 to minus 3. So I do 1 divided by that, it will be 50 hertz. So yes, 50 hertz will be the AC supply frequency. Okay, and the UK main supply is going to be 50 hertz and the voltage is 230 volts, everyone. So make sure you put this into your mind as well. So every single UK main supply is oscillating at 50 hertz, obviously AC, and the voltage is 230 volts. Right, electrical power now. So if you want to work out the electrical power of a component, it's simply going to be the current times by the voltage. So power is equal to current times by voltage over here. P is equal to I times by V, where power is measured in watts, current is measured in amps, voltage is measured in volts over here. And look, we can see that also, if you know that Ohm's law, V is equal to IR, I can replace the V with IR. It becomes P is equal to I squared R. Yes, because V is IR over there. Or if I rearrange this and say I is V over R, I can then replace the I over there. Power is also equal to V squared over R. So you've got three versions of this formula. Power is equal to I times by V, power is equal to I squared R, and power is equal to V squared over R. Voltmeters and ammeters. So a bit of basic stuff with regards to voltmeters and ammeters. The ammeter has minimal resistance to allow the maximum current to pass through it over here, and the voltmeters over here have maximum resistance, so therefore it has to stop the current from going down this branch. It has to force the current to go through there. If this one had a low resistance, the current would simply bypass the component going round. Right, so now transformers. Why do we need transformers? So first of all, we know that electricity is made at power stations and it must be transported to our homes. If the current is too high, what happens is if you pass high current through a wire, the wire heats up. It's very inefficient because energy is lost as heat. So therefore you install transformers. You either put a step-up transformer and a step-down transformer in between the power station and the home. So look what the step-up transformer is going to do. It takes the high current and it makes it a low current. It does this by stepping up the voltage. So look, it takes the low voltage and makes it higher. It steps up the voltage to reduce the current. And the step-down transformer, it will reduce the voltage, there we go, to increase the current back up again over here. So make sure you're happy with step-up and step-down transformers. And look at my summary statements over here. The step-up transformer increases the voltage to reduce the current. And look, if you look at the power formula, the voltage goes up, the current goes down for the power to remain the same. And the step-down transformer is going to decrease the voltage to increase the current back up again over here for the power to remain the same. The national grid is simply a system of pylons, cables and transformers used to help distribute electricity across the UK. It also responds to the changes in the supply and demand of electricity in the UK. So look, you've got power station, step-up transformer, a pylon, then look, then you obviously the cables going all the way from one pylon to the next, then a step-down transformer back to your home over here. So obviously the pylons are there to help hold the cables in place. And don't forget the function of the transformers is because you want it to be low current when it's being distributed, so therefore there's the least energy loss. And that's it for another session of Ceerazzle Dazzle Physics. Make sure you hit the like and subscribe button to keep my channel going, and good luck in your studies. Ciao, ciao, and goodbye.